Okay, section 11.2. This is called goodness of fit. All right, and so well, first of all, goodness of fit doesn't even sound like it's like grammatically correct, but anyway, that's what they call it. I'm trying to see if something that happens matches my expectations. So if I expect that people open their businesses equally throughout the year, and then it doesn't match my expectations because August, September, October, November, December, and suddenly towards Christmas, people all start opening businesses to take advantage of that holiday rush, maybe I'm wrong. Or maybe those numbers don't mean that much. Maybe it's not that far out. Okay, so this calculation determines whether my guess of, things open equally, it's no big deal, whether that is anything like real life. So these are observed. Then there's expected. Well, if they open equally throughout the year, so what I got to do here is average my observed. If somebody told me 120 businesses opened last year, then I would expect that that would be 10 for each month, because that would be equally throughout the year and turn into 120. So if I average my observed, I get 6.83. And so that's what I expect. Now, there's no month when 6.83 would open, but I'm going to write it down anyway. Okay, so I'm expecting basically all to be 6s and 7s, mostly 7s. But I'm going to go with the average right there. All right, then I do observed minus expected. So 4 minus 6.83 is negative 2.83. 3 minus 6.83 is negative 3.83. 5 minus 6.83 is negative 1.83. 7 minus 6.83 is 0.17. 6 minus 6.83 is negative 0.83. 0.17, negative 2.83, and then 8 minus 6.83, 1.17, 2.17, 1.17, 3.17, 4.17. That's my observed minus expected. Now, observed minus expected squared. That's the next part of the formula. Remember that when you square a negative, you get a positive. Negative 2.83 times negative 2.83 is positive 8.01. Okay. Every single one of these numbers is going to come out positive. There's no way to have negatives in this line right here. Negative 3.83, I'm going to get 14.67. Negative 1.83, I'm going to get 3.35. 0.17, I'm going to get 0.03. I'm going to get 0.69. And so on down. I'm going to get all 12 of those numbers. And then the next line says add them all up. That's the summation sign, so add them all. None of these numbers are going to cancel any of the other numbers out, because they're all positive. This is just going to keep getting bigger and bigger. And so on, until I add up all 12 of them. Okay, when I did that, I got 69.68. And then you're supposed to divide that by the expected. And the expected was 6.83. So 69.68 divided by 6.83. And I got 10.2. All right, I did all that. Okay, and what does that even tell me? Now, that is, it's a chi-squared. Okay, gosh, we have to go back to the chi-squared chart. And I'm just going to call it mine, as distinguished from the one I got from the chart. Okay, so I go to the chart, and I've got to find some degrees of freedom. Well, if there's 12 numbers across here for the 12 months, I'm going down to 11. And then I'm not going down 2 because this is not a half the leftovers situation. I'm just going down the 0.05 column. So I'm going with 11, and I'm going with 0.05, and I'm going down, and that gives me 19.675. Okay, well, what does this even mean? Okay, this is a measure of how wildly these numbers are from the center. If you think about it, if all these numbers across here were like 6, 7, 6, 6, 7, 7, 7, 7, 7, then all the little numbers down here would be like the 0.17s and the 0.83s, and all the little numbers that I would add together would be 0.03 and 0.69. Okay, so that when I did all this, I'd be adding a bunch of tiny little numbers like this, and there's no way I get to like 69. There, it'd be tiny. If these numbers very much nearly if the observed numbers very much nearly match the expected numbers, then I wouldn't even have anything to worry about. It would be so small, I'd be like, yeah, they're basically the same. So this is just measuring how wildly these are fluctuating away from that center point of 6.83. I mean, 11? That's like miles away. Okay, and that's being taken into account when I do this. And that's why my number is way bigger than if it had all been 6s and 7s across here. My number is 10.2. Now we got to look at the cutoff between good numbers and bad numbers. Small is good. Okay, small means it kind of matches what you were expecting. Big means bad. But the cutoff between good and bad is actually this number right here. So 10.2 is less than 19.675. All right, less than. And that means it's into the good zone. I didn't expect that. I thought, gosh, with that 11 over there, there's no way. But it's okay. It's all right. Those just count as minor little fluctuations nobody cares about. So, yes. This would be, it's actually failed to reject the hypothesis that they're all the same. And that's the way it always works. Your choices are fail to reject that they're all the same or reject that they're all the same. So even though I didn't write the hypotheses, this was a hypothesis test the entire time, and your choice is fail to reject that they're all the same or reject that they're all the same. And the way you're going to do it is you're going to look at the cutoff from the chart.